Look at this dashboard. On one side, we have live, undulating data waves feeding in directly from a physical machine. On the other, a structured record precisely logging every mechanical event as it happens. To get to this level of control, we are starting from a completely blank computer. By the end of this process, you will have constructed a unified interface that connects to physical hardware, tracks historical trends, and scripts accurate database events. If you want to follow along locally, you only need 3 things: a standard PC, a network connection, and a physical PLC device to act as your primary data source. Bridging these physical controllers with robust software layers takes raw machine behavior and converts it into permanent, actionable intelligence. Step 1 is deploying the foundation. You will pull the 800 megabyte executable directly from the provider's web portal and deploy it onto your local desktop. Once installed, the software hosts itself locally on port 8088. It operates on a 2-hour trial that you can reset indefinitely, giving you a continuous development environment right inside your web browser. To communicate with the hardware, the system uses an integrated OPC UA server. Think of this as a built-in universal translator that extracts raw data directly out of your external PLC. Look at this network map. The PC and the PLC must exist on the same subnet. Notice how the first 3 IP numbers align perfectly. If a single digit in that routing sequence falls out of alignment, the connection drops, instantly isolating the software. Without a perfectly aligned network, the most sophisticated control software remains entirely blind to the factory floor. Now that the connection is solid, we move into the design workspace to configure our continuous data tracking. By selecting a specific data point, or tag, and toggling its history parameter to true, the system automatically routes that live hardware data straight into the pre-configured local SQLite database. To visualize this, you simply drag a dedicated charting component onto your operator interface. The chart immediately recognizes the historical tags and begins querying the saved database records. This chart plots the mechanical sequence. As the physical machine cycles, the software actively draws every peak and valley into a live graphical trend. Continuous tracking converts volatile live signals into a searchable, permanent archive of mechanical performance. Continuous streams are useful, but we also need to capture exact discrete events, like a machine starting up or a user logging in, which requires custom SQL tables. We write a precise create table command in the database browser. This structures our ledger to track sequence runs, active usernames, and exact start times. Inside the designer, we build intermediate memory tags. These act as temporary holding cells for the event data before our scripting engine takes control. We then write a gateway tag change script using Python. This code sits dormant and only triggers the exact millisecond a specific machine sequence shifts its state. Notice this filtering process. SQL databases have rigid formatting rules. You must write a script command to manually format the raw system date into uniform year, month, day structures before sending it, or the database will throw an error and reject the entry. The script concludes with an execution command that reads those formatted memory tags and runs an insertion query, permanently pushing the data block into the SQL table. Meticulous script formatting serves as the critical bridge, ensuring raw machine events are properly packaged and accepted by strict IT databases. With the event data safely stored in the backend, we need to bring it forward to the user interface. We create a cyclical query tag, configured as a dataset. We set it to run a select all command, polling our newly built SQL table for fresh data every 5 seconds. By pulling this dataset directly onto the main operator screen, it instantly populates a user-facing table component with the live logs. If the timestamps look unreadable or disorganized on the screen, navigate directly into the table's column settings and explicitly set the date format property to properly render the values. Bridging these backend logs directly back to the front-end interface gives operators immediate, verifiable accountability of every mechanical event as it happens. Now, let's step back and force a physical trigger on the hardware to test the completed architecture. As the mechanism fires, watch the interface. The continuous chart spikes immediately to reflect the physical movement, while the digital ledger simultaneously slides down to capture a new, precise log entry. We have successfully integrated our 3 core pillars: stable network communication, live historical trending, and formatted database scripting. Mastering this integrated logic loop, connecting hardware, history, and databases, establishes the functional foundation for broader industrial automation projects.